It was really great. I don't know if it was planned, but we had our friends from Comcast up here. I would have gone right after them. What they had on their presentation was a lot of the slides that I didn't have time for in mine. I kind of was hoping for a 30-minute slot, but that was great because all the actual screenshots from the test equipment and the analyzers and all that, that's what I don't have in mind, but what we're going to talk about is automating all that stuff. So it was really good that we would have been back to back. Hello, good afternoon, Phoenix. My name is Dale Hurshowy, and I'm an engineer for Shaw Communications. Best way to reach me, if you like, is through LinkedIn. Now, I know what you're all thinking, looking at me. You're thinking, why would Canada's leading connectivity provider, Shaw Communications, invest in the automated testing of access points, and how do they do it? That's a good question. We launched our business-managed Wi-Fi product around 5 years ago, and since then, the number of APs we manage for our clients and the number of AP models we support continues to grow. Not only that, but of course, the AP revisions from the vendors are never ending. We now manage over 50,000 access points for our business clients. Today, we'll highlight some of the benefits of automation and what type of testing you can do and what the architecture is. What are the benefits of automating testing? You can test OSI layers 1 through 7. You can expect consistent, repeatable measurements. It helps eliminate human error. Helps. You have minimal training to operate, though I will add having a really good understanding of Wi-Fi and testing is advised, so you make sure that your tests are running as expected. But you don't have to understand or memorize all the different configurations and all the different knobs and all the test equipment and software and on the AP that you're going to be testing on. You'll have time to do full regression testing. You can expect a dramatic increase in your test coverage because of it. And we saw a significant decrease in our cycle time. What used to take us around 6 weeks with 30% test coverage through manual testing now takes us around 2 weeks with 80% test coverage through automation. This slide outlines the OSI layers and the test coverage. Layers 1 and 2 can be tested through things like conducted emissions and receiver sensitivity tests. Layers 3 and 4 through rate versus range and throughput tests. And use case system testing can test layers 2 through 7. These tables illustrate our test coverage for transmit, receive, and link layer tests. On the left are the receive tests, the transmit tests, such as beacon power and spectrum mask. In the middle are receive tests like adjacent channel rejection and receiver sensitivity. And finally, link layer tests like rate versus range, throughput. Here's a diagram of system/use case testing that can test layers 2 through 7. This type of testing will allow you to test connectivity, both end-to-end and peer-to-peer, roaming testing, security such as walled garden, band steering, scheduling the periodic availability of your SSID, traffic shaping, and SNMP traps. This kind of test setup requires 2 access points and 2 clients. We've automated several, but not all of this testing yet. And for our clients, we used Raspberry Pis because we found them quite easy to program compared to smartphones, though my understanding is you can program smartphones if you require it for your testing. This is a diagram of one of our test setups, rate versus range. It's a relatively simple and inexpensive test to set up. The AP is inside one RF enclosure, and the client or clients are in another. Like all of our testing that we do, except for the use case testing, it's conducted testing with cables connected directly to the antenna ports on the access point. If you're working with an AP that has internal antennas, that does require a little surgery to make that happen. iPerf is set up on both the AP end and on the client, and then attenuation is incrementally increased. When the attenuation is low, your throughput, your signal strength at your client will be high and you'll have maximum throughput. But as you increase your attenuation, your signal strength will decrease and so will the throughput. The results can be graphed and compared, and it's useful to compare different AP models or different firmware revisions. This setup can test both uplink and downlink tests. And sorry. And it's been very helpful for us. I should point out what's already up there on the side. I do have a Butler matrix on the RF enclosure with the clients. Butler matrix is very important when you do conducted testing, as it allows you every receive path on the client to hear every transmit stream coming out of the access point, and it also includes a phase shift. So it's very good for conducted testing. These are real test results from our rate versus range testing. The red small dotted line represents APA, which we tested and looked okay. As you can see, when the attenuation is low, you have maximum throughput, and as attenuation increases, throughput gradually decreases. But how do you know if it could or should be performing better than it is? I created a way to make a theoretical plot based on transmitter properties such as signal strength, number of spatial streams, and channel bandwidth. The orange line is this. I don't know if it shows up on the screen there, but it's on the model. It's on the legend. The orange line is this theoretical plot, and in this case, it was very close to the results that we saw from APA, so we were happy with its performance. The purple line is APB. That's the one on the bottom. It has from the same vendor and has similar characteristics as APA. It's just a different model, but as you can see, it performs quite poorly. So when we took these results to our vendor, they came back and eventually gave us updated firmware, which we retested that, and that's the blue line where performance came back to expected levels. This diagram represents our overall architecture of our automated testing. Robot Framework, or specifically RIDE, is the user front-end interface where you can select which tests you'd like to run and what settings you want to run with, such as access point, channel, and power. Python will have main measurement engines, such as the rate versus range test, as well as many smaller subprograms to control all the different test equipment and software involved in your testing. Robot Framework and Python are free. Then you have test equipment, which I say is the opposite of free. It can range from $1,000 or so for a programmable attenuator or RF switch to tens of thousands for a signal generator or an RF analyzer to hundreds of thousands of dollars for an Ixia variant chassis. And your AP, of course, needs to be controlled, be it through API, WLC, or web page dashboard. And a database is essential for collecting the large amounts of data that's going to be generated through your automated testing. The nice thing about automation is it allows for the automating of reports and pass-fail matrices, which would take significant time if you were to do those manually. From our experience, I wouldn't even suggest really starting the automation process unless you're willing to set up a database, because you're going to have a lot of data. This is a screenshot of RIDE, Robot Integrated Development Environment. It's the GUI editor for Robot Framework. In this example, it's the rate versus range test that we talked about earlier. On the left-hand side is where you can check off which test you'd like to run this time. And on the right are different parameters that you can edit if you like, such as iPerf settings or AP, channel, and power. This is a block diagram for one of our main RF test chambers. On the right is the AP with several jumpers for both 2.4 and 5 gigahertz. Then an RF switch to switch between the bands. Then some more splitters and attenuators. Then on the left, you can see a variable attenuator and another RF switch to switch between different pieces of test equipment that are outside of your chamber. On the bottom is a signal generator and RF analyzer. The signal generator can create both Gaussian noise and Wi-Fi signal and inject it both in the uplink and downlink. One reason why you might want to inject noise is to force your AP to transmit at a specific MCS rate. And the signal analyzer analyzes the signal from the AP for various different testing. Here's some photos of the front and back of that chamber that we just saw the block diagram for. And on the inside, you can see the AP sitting on top of the board, connected to a few jumpers. And all of the plumbing is underneath the board, and it is never touched as it's fully controlled through automation. And I'll add that you don't have to complete full automation right away when you start. If you start off with the right type of architecture, you can just begin with the basics. And then from there, you can refine your work and add more and more tests as time goes on. Thank you.